right, welcome back. So in the last series of videos, we were looking at hypothesis testing for proportions, right? And we were sort of orienting ourselves around this idea of a null and an alternative hypothesis. And we'll go collect data, right? And we want to see if we have enough evidence to support this and reject this, right? Where this is sort of the status quo, the null hypothesis is the status quo. We have some challenging information that we think might set a different status quo. Maybe, right? So what that does, though, we use that z-test to figure out if we had evidence against the null here. But all that tells us is whether we have evidence against, right? We use that p-value to sort of answer that question. But what that does not tell us is sort of the size of the effect, right? This is what we're going to be doing in this video with confidence intervals. Okay, so just a quick recall, kind of summarizing everything again. Testing a hypothesis only tells us whether or not we have a good claim, right? But what we want to do is eventually bring it back and put it in relation to the population, right, based on our sample. And we're going to use these confidence intervals to do that. It's pretty cool, actually. So what we're going to do is compute a range of values that will probably contain the true population value, okay? So it'll be some sort of thing that'll look like this, where it's like, I don't know, two numbers or whatever, right? And somewhere in this interval is the actual population estimate, right? So we're not really able to get a spot on number, which is fine, but we are able to get a range, which is more popular and a little bit more, I think, easier to understand. Also, very much sort of the norm in statistics, or at least what you see out in the news, right? Okay, so that's what we're doing. We're computing a range of values that will have the true population somewhere in there. Okay, a little bit about confidence intervals is that we are limited to 0% to 100% confidence level. What the heck does that mean? Well, I'll tell you here in just a second. But there's a little asterisk here, because this idea of a confidence level is more or less this formula. Okay. Now it's not something that you'll ever have to calculate. It's just always kind of given. So for instance, if we are given, let me use a different color. Whoops. So let's see, if we're given an alpha of 0.05, based on this little thing over here, our confidence level will be 0.95. And both of these can be kind of translated into percentages like so, right? So a 95% confidence level means that we're using an alpha of 0.05 and vice versa, okay? Now, what the heck? I put this little asterisk here for a reason. It's not... This sort of range here is not exactly 0 to 100%. Because if we had a 0% confidence level, that would mean that we would have to have an alpha of 1, right, for this thing to kind of work out, right? Which is never going to happen, right? Never will happen. Same thing in the other way, too. If we had a 100% confidence level, that means that we would have to have an alpha of 0, which never occurs, right? But we can get kind of close. We can get close to 100 and close to 0, but never exactly, right? So it's more of this kind of thing. Okay. Another thing, too, that sometimes gets a little bit convoluted, or at least people get confused, this idea of confidence intervals, usually we stick with 95%, just kind of like how we stick with an alpha of 0.05. Same logic, right? Just sort of saying the same thing. What a confidence interval does not represent is some percentage of data, right? It's not 95% of the data, right? It's something a little bit different, a little bit more nuanced, okay? But really do make sure that you don't get, you're not defining a confidence interval as this, because that is not what it is. So here is the general anatomy of a confidence interval. It is actually not too hard. there is a little bit of math involved. Here, whoops, here and here. Typically, this statistic can be anything. We've been doing a ton with proportions. Actually, I guess it's just P. But we can use, we can make confidence intervals for a mean. In fact, we can even make them for standard deviations. We can make them, we can make them for medians, modes, all that kind of stuff. We just need to know the formula for this, which in this context I will give you always. Okay, so this statistic can be anything, right? We've been working with proportions because they're easy. It's a good introduction into the idea. And then plus or minus, sorry, not plus or minus, plus and then minus, right? So we're going to get two values that sort of show up as this, right? So we have a lower bound and an upper bound, okay? And that's it. So it really is just a bunch of arithmetic, really. This will always be given to you. I have a nice little table lining that out. This has its own formula, and this is something that we've already done, right? Where we might be testing, we might be doing a hypothesis test for a p-hat, right? A sample proportion, and then it turns out that, we have evidence against the null, and then we want to say, all right, since we have evidence against the null based on this new value here that we calculated and that we collected, what is the population range, we'll say. And then based on the question, you'll use just one value for this. And then based on the context, in this case, we have a standard error for proportions, which is pretty easy to calculate, I promise. So again, statistics can be any estimate. The z-crit is just a value that is found on the z distribution that I will give you. There's a table that I've got. It's totally based on the confidence level. So, there's some math that you could do. I think it's stupid to go out and find a new z-crit every single time when there's really only, in this case, usually 0.05 for alpha or 0.01 or maybe 0.1. That's about it, right? So I'll just give you those values, and that's that. And then this idea of standard error just kind of goes back to the idea of the central limit theorem, where we can assume that our proportion or our sample mean or whatever comes from a distribution that looks like this. And we know that if we have a high sample size, we get closer and closer to the population. That means that our error, sort of the average distance away from the population, is going to be low, right? If we have a high sample size, standard error will be low, which is good, which is what we want. But if we do not have a high sample size, standard error will be high. And that's not a bad thing. That just means that our interval will be very wide, and not too precise. Okay, here's the table. Here it is for the z-scores, for that z-crit. Okay, so this one I've got sort of highlighted here is the most common, right? So alpha is just a convention, right, that it's always 0.05. Well, it's not always 0.05, but it's very frequently 0.05. That means that our confidence level, we're going to be making a 95% confidence interval based on this 95% level. And then in the formula, this you just plug in 1.96. Easy peasy. If for some reason the alpha is different, if you say use an alpha of 0.01, that means your confidence level will be 1 minus 0.01, which is 0.99, and you will use a z-crit of 2.56, right? And this is all derived from that z distribution that we've worked with all the time. Also, these are the two most common, these two right here, where these, show up every now and again. It's good to know what these values are, but these two are sort of the major convention in statistics. Okay, so that's that one part. That's this part that's a little bit new. We know this. We've probably already calculated that, or it's given to you. Now we've got this, and then now we just got to kind of define this a little bit better. So standard error is just the average difference of all possible random samples, right? So if we recall central limit theorem, actually we can go back even further, we've got this chocolate chip cookie, or blueberry muffin, I guess, that represents our population. The whole idea with statistics is that we want to grab a sample that's representative and suitably random, right, that kind of thing. And that's large enough to say, all right, we've probably gotten close, right? So in this case, right, we've got a sample size of, let's say, n equals 20. We got 20 of them. Whereas if we did it again, I'll draw the whole thing again. Blueberries. And then we grab maybe these 4 or something, just sort of guessing. I'll say n equals 5 to make everything kind of nice. The standard error here, we've gotten closer to the overall population here than we have here, right? So the amount of error, sort of the amount of stuff left over, is much lower with the bigger sample size than here, right? So in this case, we've got less average difference here away from the population statistic, whatever it may be, than we do here. We've got so much more room to wiggle to where we have to account for that in our estimate, right? So that's the general idea there with standard error. It is only accounting for sample size, right? The bigger the sample, the smaller the error is. The smaller the sample, the bigger the error is. And that's that, right? Very similar to standard deviation of a sample, just a slightly different context. Instead of looking at the nature of one sample, this is looking at the nature of all possible samples based on the central limit theorem and this idea of sample size and population. Again, details that are not like totally, you don't really have to worry about getting hung up with them, but good to have in the back of your head, especially this idea of sample size going up means the error is going down. And then on the other hand, sample size going down, standard error is going up. And that's that, right? So take this home. Take that home, please. Don't sell it. Show it to your family. Okay, so when you're done constructing an interval, a confidence interval for whatever statistic in whatever context, this is generally the idea or the type of sort of rhetoric that you want to use. So let's recall that you get some, I'm just going to throw out 2 random proportions that may be part of, some test that we've done. All right, so this is our confidence interval. We'll say this is our 95% confidence interval. Let me write that to you. CI. CI is short for confidence interval. Again, 2 totally random values that I picked. But in this case, we would say we can be 95% confident that the true population, in this case I picked a proportion, right? True population proportion is between 0.45 and 0.55. Okay. We are 95% confident that the true population proportion is between 0.45 and 0.55. Well, what the heck does this 95% confident mean? Well, it's kind of like another word or another sort of saying for probability. So, in this case, we are sure that if we were to do this experiment or whatever, if we were to do this experiment, let's say 1,000 times, 950 of those times, whatever thing we're measuring, this population parameter, whatever thing that we're interested in, 950 of those times, that thing will be between these 2 values, right? If we did it 100 times, 95 of the times, the thing that we're measuring will be in between these 2 values. And then the other 5 times, they will maybe be outside, okay? And that's that, right? This is all sort of related to p-values as well. We'll see more of that in an example. I'd rather not go into all of the kind of math theory behind it. But that's the general idea, right? So 95% confidence means that if we were to do this an infinite amount of times, or like a super large amount of times, we kind of repeat this experiment over and over again with a different sample, slightly different sample, then 95% of those times will result in some value being between those two values. Gosh, my phone is blown up. My power went out earlier today, and so I think that's what it is. But we're good. We're good. Okay, so talked about the interpretation. Talked about the confidence level, sort of what that means, right? And we can change this too. We can change this. But what happens? What happens when we change the confidence level? Well, friend, that is a great question. So the higher the confidence level is, it turns out the wider the interval becomes, okay? So in this instance, a 99% confidence interval will be wider than a 95% confidence interval, okay? So when the confidence level goes up, the interval becomes wider. And that sort of like encapsulated here. The higher the confidence level, the more certain your interval, so the higher the confidence level, right? You are saying like, okay, I've really covered my butt here, right? I'm very confident that the value is going to be somewhere between the lower bound and the upper bound, right? However, since it is wider, and since you're saying you're more confident, you're going to be less precise overall, right? Overall. And the opposite is true too. An 80% confidence interval will be narrower than a 95% confidence interval, right? So you're saying that you are less certain that it's between these two values, but you are going to be more precise because it's narrower, right? So you're leaving a little bit more up to chance, in that case with an 80%, confidence level or confidence interval. You're leaving 20% up to being wrong. Or if you were to do the experiment again a ton of times, 80% of the times will result in, whatever thing you're looking at, it's going to be between these two values, but 20% of the time it won't be in there, right? So it's this sort of like give and take. That's why more or less we use 95% actually I guess it's kind of arbitrary, but we're okay with 5% of the time being wrong, right? If we were to repeat the experiment however many times, 5% of the time we're all right with not getting it spot on. Okay, so that's the sort of English idea, but let's take a look at the math. Let's take a look at the math and sort of why that makes sense, or why I think it makes sense, and why I'm gonna try to get it across. So we have this idea, and let's look at a 95% confidence interval. Okay, so again, we are estimating the actual population, right? We're bringing it all the way back, right? So we have our formula, looks like this. So one component looks like this, where we've got the standard error being multiplied by some z-critical value, okay? And since we're looking, and then we've also got the same thing, but we're subtracting instead. Okay, so I'm just saying we're working with proportions here, easy to work with. I'm not even going to provide a standard error. I'm just going to leave it as is, right? So we can see sort of how this stuff makes sense. So with a 95% confidence interval, we're 95% sure that the actual population estimate, whatever it may be, is between this value and this value. Okay, so with a 95% confidence interval, what we need is the appropriate z-critical value, which in this case would be 1.96 in both spots, right? So that leads to some lower bound, we'll call it LB, and some upper bound, UB. Okay, dope, no doubt. Let's see how this changes with a 99% confidence interval. Keeping everything else the same, right? We're not going to worry about, let me kind of block this off. We're not going to worry about the standard error. I'm just using the proportion here. And actually, if I'm being specific, it's just P. P hat represents the sample. P in this case, we'll just say, represents the proportion of the population. The population proportion. Good Lord. I don't think I've had enough coffee today. Okay, anyway, so you can kind of already see where this is going, right? We still have these two components. And then we have our standard error, right? Standard error. But in this case, with a 99% confidence interval, we need to be more sure. We need to be more sure that our estimate is going to be somewhere in there. So in that case, we're going to use 2.56, right? So essentially, what's happening here is that when you multiply these two values together, right? Since this 2.56 is larger than this 1.96, right? This is going to result in, we can kind of visually see it maybe, where we have our P, right, our proportion. In this case, let's say that this, we can actually do it this way, right? Our values that are contained within the upper and lower bound here might look something like this. And then this is because we're multiplying by a larger number with a 95% confidence interval. Since we've got a smaller number being multiplied here, that means we're not going to be as far away from this, right? We're not going to be moving as far. So it might look something like, I don't know, here, right? Kind of this idea, right? So the higher the confidence interval, the higher the confidence level, means that we have to use a higher z-crit to include more values so we can be certain, right, that we at least got it, right? We're going to be less precise, but we are going to be really covering our asses here, right, with this 99%, because we're going to be including more values than we would with the 95%, right? That's the kind of idea. How about we do one more example? Yeah. One more example, and then I'll actually show you how to do this stuff in real life. Okay, so here's a dartboard, okay? And generally the goal, I'm pretty sure, is to hit the bullseye, right? Hit the bullseye. But let's say, instead, we've already, we don't really care about the bullseye right now. Let me use a darker color too, or a brighter color. Let's say that we don't care about hitting the bullseye, and somebody comes up to us and says, hey, how confident are you that you can hit the dart somewhere in this range, right? So it's somewhere kind of in this area right here. I'd say pretty confident, right? I'd say pretty confident. Okay, so then this person says, all right, if you were to do this, if you were to throw a dart 100 times, how many times would you hit this area? Great question. I'd say maybe, I don't know, I'm not great at darts, but I'll say maybe 95 out of 100 times I could get it somewhere in this area, right? And that's all we care about. That's the same idea with confidence intervals. We don't care about the bullseye. We care about getting close, right? Close. We're just going to get, I guess close only counts in horseshoes and hand grenades, but in this instance too, right? We don't care about the bullseye. We just care about getting somewhere in this region, right? Okay. So then that same person comes up to you and says, all right, forget this bigger spot. What about this area? What about this area? How confident are you? Or if you were to do this 100 times, how many times do you think you would be able to hit somewhere in this area, right? We don't care about the bullseye. It just so happens that the bullseye is in this area, right? But we don't care about hitting it spot on. We just care about the area. Well, then they ask you, again, how many times out of 100 could you hit somewhere in this range? And I don't know. Shoot. Maybe 80 times? Still, I'm kind of giving myself more credit. But we can kind of see that since the area is now narrower, we are less certain that we'll be able to hit somewhere in this area. The bullseye is still in there. But we are more likely to kind of hit out here too and not get it, right? So this area is a bit more precise, bit narrower, right? The bullseye's still in there, but we're leaving a little bit more up to chance by hitting, out here, wherever it may be. And that's the general idea with confidence intervals as well, right? The more confident we are, the larger the interval, the more confident we are that we got it, right? The bullseye's still in there, but also we're really covering our ass. But as the confidence level decreases, so does this area that we think we're able to hit. Bullseye is still in there, right? The true population, whatever, statistic is still there, but now we're given a smaller range. We're going to be a little bit less confident, a little bit less certain, right? And that's the general idea. So with all of that being said, because I didn't really show you many formulas, at least specific to proportions or whatever, so let's move on and let's actually see how all this works. So I'll see you there in just a little bit.